All right, hey y'all, Dr. Hines here, going to talk about the molar volume of a gas lab. Just going to give you a little bit of some basic background so you understand kind of the concept of what's going on. In class, you've probably talked about some, I'll just say, simple gas laws, like, for example, Boyle's law, Gay-Lussac's law, Charles' law, and the law that we're going to deal with today is Avogadro's law. All right, so Avogadro's, and we're talking about gases here. We're talking about gases. And the idea behind Avogadro's law is that the volume of a gas is dependent upon how many particles are present in it. And of course, you know Avogadro's number, the 6.022 times 10 to the 23rd. That's how many particles of gas you would have if you had 1 mole. And that would occupy some specific type of volume. And it doesn't depend upon the identity of the gas, okay? All gases are going to behave the same way. If you have the same number of particles, it's supposed to have the same volume of gas. So his law was all about mole and volume. And of course, in the gas law realm, when you talk about moles of gas, we typically use the symbol N for that. And then for volume, you just use what you might expect. You would use a V for that. So the idea is that if you change the number of particles, you should change the volume of the gas, as long as maybe what I should do is I should write it like this. I'm gonna erase this right quick. So these two things should correlate with each other. So if you basically take the ratio of N over V, okay, increase the number of particles, you're going to increase the volume. So in theory, this should be a constant value. All right, as long as temperature and pressure are held constant. So that's what's going to make what's going to make this ratio work. And essentially, what we're going to do in today's lab is we're actually going to synthesize. We're going to synthesize a specific number of moles of gas. We'll measure the volume of this gas. And what Avogadro found is that regardless of what the gas was, erase this up here, Avogadro found, and hopefully you're going to get this as your experimental result, all right? 1 mole of any gas at something called STP, it's going to occupy 22.4 liters, and this is hopefully what you're going to find out in lab. Now, to kind of finish off this discussion a little bit, like I said, we will prepare a specific number of moles of gas, we'll measure its volume, and we need to make sure that it's at what we call STP. STP stands for standard temperature and pressure. Erasing this down here. So it's a numerical definition. I mean, yeah, it's a word definition, but it's also a numerical definition. So standard temperature and pressure. Okay. Standard, some sort of value that everybody would use to be able to compare their results against each other, okay? So if we all select a standard temperature, we can compare our results and see if they're similar or not. Standard temperature for a gas, probably talked about it in your lecture a little bit. That's equal to 0 degrees Celsius. But you know, in the gas law stuff, you really shouldn't be working in the Celsius temperature scale. You really need to be using the Kelvin temperature scale. And that's going to be 273 Kelvin. And when we do some calculations, we're definitely going to be using the Kelvin scale on this. But anyway, if we all do this experiment, we're going to compare it to the result of, you know, at 0 degrees Celsius, which is kind of chilly, by the way. I mean, this is pretty much like the freezing point of water. Not saying this is a comfortable temperature to work at, but we're going to be able to calculate a result as if it was at 273 degrees Kelvin. And then standard pressure is just equal to 1 ATM. A typical normal day would be about 1 ATM plus or minus as the weather changes from day to day. But so we're going to be recording temperatures, we're going to be recording pressures, we're going to be recording moles, we're going to be recording volume, and hopefully when all is said and done, when we do all this math, we'll just see how close you all get to this 22.4 right here. All right, so from here on out, we're going to start off with the experimentation portion of it.